So the first talk will be by Hannes Rüter. He will talk about merger of dark matter and mixed neutron stars.
Okay, thank you, Richard. So let me start with a scenario that Tim was basically introducing just in the previous talk. So we have two orbiting neutron stars, and these neutron stars are not only made of baryonic matter, but they also have dark matter. And we model the baryonic and as well as the dark matter as two ideal fluids that move without any direct interaction between them. So in reality, maybe there might be some small interaction between dark matter and baryonic matter, but here we are focusing on the physics of the in-spiral, where we assume we can neglect this potential interaction. So the energy momentum tensor in this case is just the sum of the two individual fluid energy momentum tensors that we all know. And in this talk, I will basically show you some results for three distinct configurations. One configuration is the single fluid configuration, where we have just a purely baryonic neutron star, so no dark matter at all. The second configuration is what we call the dark core configuration. So in this configuration, the dark matter is only confined to the core of the neutron star, and for this case we use the equation of state for the dark matter that is corresponding to an ideal Fermi gas of particles with 1 GeV, and in this case we use 5% of the mass for the dark matter. And yeah, I have some illustration for this case. So the blue spheres would be the surface of the baryonic fluid, and then I've cut a little hole inside so that you can see inside there's a little ball in black that is the dark matter. Okay, and the third configuration that we consider here is the dark halo. In this case, the dark matter cloud extends kind of beyond the surface of the baryonic core, and for that configuration we use an equation of state with particles of a mass of 170 mega electron volt. And in this case we only have 0.5% of the mass of the star being dark matter. And yeah, an illustration for this case, so the grayish and black shade is the dark matter. You see it extends beyond the more colorful baryonic matter, and what we show here is the specific enthalpy of both the baryonic matter and the dark matter. And what you also see are these black lines which actually indicate the grid layout for, or a numerical grid on which we solve the initial data that we construct for these stars. What you can also appreciate in this illustration is that there's a slight deformation of the stars. So we put the stars quite close together to emphasize the tidal deformations that the two stars exert on each other. And actually our grid, you see, is still, although it's X-shaped, our grid is following the shape of this surface, and that's because we use so-called surface-fitted coordinates. Okay, so those are the three configurations we have. Now let me briefly talk about the scenarios, how such configurations could come about. So we have already heard about dark matter capture during I think some talks yesterday. And if you consider the scattering cross-section between dark matter and baryonic matter is 10 to the minus 45 centimeters squared, that's a typical number, then on the lifetime of the binary, you could accrete like about 10 to the minus 10 solar masses for a dark matter core. So that's usually not a lot. Maybe you can play a little bit with the numbers of the scattering cross-section or the density of dark matter and the surrounding medium, but you shouldn't expect a lot. But another scenario is actually that there could also be dark matter that comes from primordial overdensities. So you could imagine after the Big Bang, there's an overdensity of dark matter, and that is actually then also the seed for the baryonic matter to accrete on this potential. And yeah, over the many years of the stellar evolution, the dark matter, of course, stays around and could make up the dark matter core. So yeah, Tim also gave already a strong motivation where we should look at this. So we want to see, of course, the imprint of dark matter on gravitational waves. And some other papers have already studied this and said in these two component binaries, or two component star binaries, there seems to be generally a so-called one-arm instability that one couldn't see then make an imprint on the gravitational wave signal. And there's also a paper by Bauswein and friends who checked whether, for example, advanced LIGO could see such a signal, and they come to the result that advanced LIGO could see a dark matter core of 0.1 solar mass, and Einstein telescope even a dark matter core of 0.01 solar masses. Okay, so now I come to the first part of our results. So I'm constructing initial data for the system. As Tim already introduced, we have to solve some metric constraints. Those metric constraints give us a set of PDEs that in this case is formulated in terms of the so-called extended conformal thin sandwich equations. Those give us 5 PDEs, and from these 5 PDEs, the solution is the lapse, the shift, and the so-called conformal factor. And then to put the neutron stars in equilibrium, we come up with 2 additional constraint equations that kind of govern the quasi-equilibrium, the quasi-equilibrium constraints, and they give us, as a result, the velocity potentials, phi, and because we have 2 fluids, we have potentials for 2 velocities, so this gives us then 2 elliptic partial differential equations. And I've implemented then this 2-fluid system into an already existing code that is called SGRID. So SGRID is a spectral code, so it uses a spectral discretization to expand the fields. It has these nice surface-fitted coordinates, and it is then applying an iterative procedure to obtain a solution to this PDE system. And yeah, I show you again this figure. So in this figure, I show you, for example, the conformal factor that illustrates kind of the curvature that we have in this configuration. And this conformal factor is one of the output of this procedure. So now an interesting problem to consider here is, or an interesting question to consider is, whether the dark matter and the baryonic matter will actually move with the same velocity. So if you have an isolated star that is non-spinning, then it's clear, okay, both components are not spinning, they have the same velocity. But in a binary, the concept of a non-spinning binary is a little bit more involved. And here we consider these non-spinning fluids, or also called irrotational fluids. And yeah, to get a sense of how different the velocities are, I first construct what I call residual 3 velocity. So I compute the 3 velocity, that's basically this term, and then I subtract the velocity that governs the orbital rotation, so that I'm basically transforming into the co-rotating frame where I follow the motion of the stars. And then you see, okay, the residual velocity is this. It's about, yeah, maybe up to 0.05 times the speed of light. And the relative difference between the two fluids is up to 10% actually in this residual velocity. So they are not moving with the same velocity. So now, since the time is already coming close to the end, I go quickly to the evolution. So for the evolutions, we use a BAM code. The BAM code, there we use a Z4 formulation for the metric evolution. I've implemented this 2-fluid hydrodynamics. So there was already something implemented by Mattia Emmer, as Tim pointed out, that was implemented for mirror dark matter, but now it's extended to arbitrary equation of state for the dark matter. And the impact of this constraint-solved dark matter is actually, constraint-solved configurations is actually important. So here I show you the dashed blue is just a superposition of TOV solutions, and you see there are very large oscillations in the density, but if you solve everything for quasi-equilibrium, you have no artificial oscillations, and that's really important if you want to see the small imprint of dark matter. So now let me bring up a video. So, Tim. Sorry, what? Restart the video. Okay. So Tim has already shown this video. I go a little bit closer to the merger. So now what you see is the black spots are the dark matter. They actually merge a little bit, the dark matter cores merge a little bit after the baryonic matter. Then both components have merged. And yeah, you have some kind of ring down or metastable state of the neutron star remnant. But now I also want to draw your attention. So this is now the merger phase. So the baryonic matter has already merged. But what you see is now that actually the rotational velocity of the dark matter cores is different from the rotational velocity of the baryonic matter. So you see kind of that if you look closely, it's a little bit faster. So, and that means the dark matter should emit gravitational waves that have a different frequency than the baryonic remnant. Here. No. Here. So visualize. Okay, so we get this waveform. I don't go into details of the waveform because you have just in spiral and ring down. But now what you can see in the power spectral density is the emergence of this. So you have this main peak from the remnant, and then you have this new side peak that we attribute to the higher rotational frequency of the dark matter. So that's the end. Thank you very much.
Sorry, we are a bit over time, so if a quick question. There's 3 questions at least. I think Daniela went first.
Thank you very much. Congratulations for succeeding with the initial data. I was wondering, so you showed how the proper initial data and the approximate one behave in terms of densities, but what about in terms of waveforms or the presence of, I mean, the phenomenology, for example, the presence of this one arm instability? So what you could not get before and you are getting now, and what stays the same? I'll be just curious.
With respect to the, okay.
With respect to those simulations with superimposed.
So we have done some comparisons, but it seems to be just very different. So everything merges at different times. So yeah, it's really hard to compare those two because it really has a quite a big impact.
So it's not a fractional difference of 50%, but it's really different if you put the proper initial data here.
Yeah.
So I think just because we are almost 5 minutes over time, it's better to move to the next speaker.